we will have to study about the chemical properties. Chemical properties. So, a carboxylic acid has a carbonyl group, a hydroxyl group and an alkyl or aryl group attached to the carbon atom. So, it can undergo different types of reactions. There are reactions involving the cleavage of OH bond, there are reactions involving the cleavage of CO bond, reactions with respect to the carboxyl group and also reactions with respect to the alkyl or aryl group attached to the carboxyl carbon. So, first we will study about the reactions involving the cleavage of OH bond, cleavage of OH bond. So, in that we are going to study about the acidity of carboxylic acid, acidity of carboxylic acid. The first reaction is reaction with metals. Just like alcohols, phenols, carboxylic acids can react with metals liberating hydrogen. A carboxylic acid molecule reacts with a metal like sodium to form the sodium salt of carboxylic acid with the liberation of hydrogen gas, which is similar to the reaction of alcohols and phenols. Carboxylic acid can also react with strong bases like sodium hydroxide to form RCOO, Na and water. That is an acid reacting with a base to form salt and water. So, this reaction is undergone by phenols, but not by alcohols. Alcohols do not undergo this reaction, whereas phenols as well as carboxylic acids undergo this reaction. So, you can say phenols and carboxylic acids are more acidic than alcohols. Another reaction of carboxylic acid is with weak bases like sodium carbonate and sodium bicarbonate. So, when carboxylic acid reacts with sodium carbonate, it forms RCONA forms water and liberates carbon dioxide. Similarly, it can react with sodium bicarbonate to form RCONA with the formation of water and liberation of carbon dioxide. So, here sodium carbonate as well as sodium bicarbonate, they are weak bases. So, only carboxylic acids can react with weak bases, whereas alcohols and phenols do not react with these compounds. That is why you can say carboxylic acids are more acidic when compared to alcohols and phenols. So, these two reactions can also be used as a test for carboxylic acids. So, when an organic compound is given to you and you are asked to detect the presence of carboxylic acid in it, you can just treat them with sodium carbonate or sodium bicarbonate. So, if there is effervescence due to the liberation of carbon dioxide, then you can say the given organic compound has carboxylic group in it. So, the acidity of alcohols, phenols and carboxylic acids can again be compared by taking their resonating structures. So, you know alcohols when dissolved in when added to water, it forms RO minus and H3O plus. That is because alcohol has an ability to donate a proton which is accepted by water. It forms RO minus, an alkoxide ion and H3O plus ion. So, here the R group shows the plus I effect, that is it is electron releasing. So, because of that the electron density on oxygen atom increases and it destabilizes the alkoxide ion, because of which this can again attract the proton. So, this is in case of alcohols. Alcohols when in water they have the ability to donate proton, they form the alkoxide ion, but the R group in alkoxide ion is electron releasing, because of which the electron density on oxygen atom increases and this alkoxide ion gets destabilized, because of which it will attract the proton once again and the reverse reaction might take place. But in case of phenol, even phenol when added to water, they can donate proton. So, they form phenoxide ion along with H3O plus. Here the benzene ring is electron withdrawing. So, the negative charge on the oxygen atom can be delocalized in the benzene ring. So, you can write different resonating structures for it. Take it here. So, the negative charge shifts here. So, this also shifts here. So, these are the different resonance structures. So, here the negative charge again shifts to this. In this way you can write different resonating structures for the phenoxide ion, but all these are non-equivalent resonance structures. That is because the negative charge is being delocalized between the more electronegative oxygen atom and the less electronegative carbon atom. So, always the negative charge here is delocalized between the most negative electronegative oxygen atom and less electronegative carbon atom. So, you can say even phenoxide ions are not that stable, but they are more stable than the alkoxide ion. But when we go for carboxylic acids, even they when added to water, they donate a proton, they form RCOO minus and H3O plus. This RC double bond O can that is the carboxylate ion can be written like this. So, here this shifts here. So, you can write resonance structures like this and this bond will shift here. So, this carries a negative charge and the hybrid you can write it as resonance hybrid is written like this. That means the negative charge is being delocalized between two electronegative oxygen atoms here. So, when this oxygen atom having a negative charge, the negative charge is shifted here, this negative charge will be shifted to this oxygen atom. So, you can say that the negative charge has been delocalized on two electronegative oxygen atom. So, this is more resonance stabilized when compared to the phenoxide ion as well as the alkoxide ion. So, you can say carboxylic acids are more acidic when compared to alcohols and phenols. So, next we will study about the pKa values. So, pKa values they help in comparing the acidic strength of carboxylic acids. So, we will again consider the same reaction, that is when carboxylic acids are added to water, it forms the resonance stabilized carboxylate ion and H3O plus ions are formed. So, applying law of mass action, you can write K equilibrium, it is equal to the concentration of RCOO minus into concentration of H3O plus by concentration of RCOOH into concentration of water. So, here you can write Ka, it is equal to K equilibrium into concentration of water, it is equal to concentration of RCOO minus into concentration of H3O plus by concentration of RCOOH. So, where Ka is called as the dissociation constant of an acid. So, for convenience we are going to express Ka in terms of pKa. pKa is nothing but negative logarithm to the base 10 of Ka. It is seen that trifluoroacetic acid is the most acidic carboxylic acid, and the pKa value of it is found to be 0.23. This is for fluoroacetic, that is trifluoroacetic acid CF3COOH, and for benzoic acid C6H5COOH it is found to be 4.19, and for acetic acid it is found to be 4.76. Here you can see lower the value of pKa, stronger is the acid. So, I have already told you trifluoroacetic acid is the strongest of carboxylic acids, and so it has a pKa value of 0.23, whereas benzoic acid has 4.19 and acetic acid has 4.76. So, when we compare the pKa values of these two, you can say benzoic acid is a stronger acid than acetic acid because it has low pKa value. So, carboxylic acids are weaker when compared to mineral acids. pKa value of hydrochloric acid, it is found to be -7. So, lower the value of pKa, stronger will be the carboxylic acid. So, next we will study about the effect of substituents on the acidity of carboxylic acids. Effects of substituents. Effect of substituent on acidity of carboxylic acid. So, substituents affect the stability of the conjugate base and thus they affect the acidity of carboxylic acid. Suppose an electron withdrawing group is attached to the carboxyl group. So, this is going to withdraw electron and it is going to stabilize. We will take the suppose an electron withdrawing group is attached to the carboxylate ion. So, this is going to withdraw the electron towards itself and hence the carboxylate ion becomes more stable and hence the acidity of carboxylic acid increases. Whereas, an electron donating group if attached to the carboxylate ion, so then it donates electron and it destabilizes the carboxylate ion and hence the carboxylic acid becomes weak. So, we will see how some of the groups affects the acidity of carboxylic acids. So, phenyl group is less acidic when compared to all the halo groups, that is the iodo group, the bromo group, or the chloro group, or the fluoro group. So, if these groups are present present in a compound, and if phenyl group is also present in another carboxylic, so phenyl group is less acidic when compared to the halo groups, and the halo groups are less acidic when compared to the cyano group, and cyano group is less acidic when compared to the nitro group, and this will be less acidic when compared to the CF3 groups. So, here you can see the phenyl group is least acidic and the CF3 group is most acidic. So, depending on the pKa values, we can just go on arranging few of the carboxylic acids in the increasing order of their acidity. So, we know trifluoroacetic acid, acetic acid is more acidic when compared to CCl3COOH. This is more acidic when compared to CBr3COOH. So, this will be more acidic when compared to CnNO2 CH2COOH, CF3COOH is more acidic when compared to CCl3COOH. Then this is more acidic when compared to CCl2 CH2COOH. Then this is more acidic when compared to NO2 CH2COOH. This is again more acidic when compared to CN CH2COOH. Similarly, now when we have just one fluorine atom in the methyl group of acetic acid, so this is more acidic when compared to Cl CH2COOH, Br CH2COOH. This is more acidic when compared to HCOOH, and this will be more acidic when compared to Cl CH2COOH. The C6H5COOH will be more acidic when compared to C6H5CH2COOH, and this will be more acidic when compared to CH3COOH, and this is more acidic than CH3CH2COOH. So, now here you can see we have a fluorine. There are 3 fluorine atoms instead of the CH3 group of the acetic acid, trifluoroacetic acid. So, since fluorine atom is electron withdrawing, the acidity increases. So, chlorine is less electronegative than fluorine. So, trifluoroacetic acid is more acidic than this compound. So, here again there are just 2 chlorine atoms. So, here there are 3. So, this is more acidic than this. Then we have a nitro group. Nitro group is more acidic than the cyano group. So, now as the number of fluorine atom decreases here, so this is less acidic when compared to all these. So, whereas it is more acidic than Cl CH2COOH. So, here followed by formic acid. So, here you can see the distance between the carboxyl group and the chlorine atom, electronegative element, goes on increasing. That is why the acidity goes on decreasing. So, phenyl group is attached to a carboxyl group here. It is less acidic when compared to all this, but more acidic than phenyl acetic acid. So, again the phenyl group is away from the COOH group, there is a CH2 group in between these two. So, acidity decreases when compared to this, and here we have a methyl group which is electron releasing. So, that is why the acidity decreases. So, this is again an alkyl group which is again electron releasing, and hence the acidity decreases. So, then coming to few of the aromatic carboxylic acids, we will see the acidity of aromatic carboxylic acids. What is the effect of electron withdrawing group as well as electron releasing group on the acidity of benzoic acid. So, this is benzoic acid. So, suppose we have an electron withdrawing group here, NO2 group is electron withdrawing. So, what happens is the acidity of benzoic acid will be increased. It is because of the electron withdrawing nature of the nitro group. And suppose there is an electron releasing group like the methoxy group attached to the benzene ring. So, then the acidity of benzoic acid decreases. So, you can say para-nitrobenzoic acid is more acidic than benzoic acid, and this is more acidic when compared to para-methoxy benzoic acid. This is also seen in their pKa values. The pKa value of benzoic acid is 4.19, and that of para-nitrobenzoic acid is found to be 3.41, and that of para-methoxybenzoic acid, it is found to be 4.46. So, from this you can say lower the pKa value, stronger is the acid. So, para-nitrobenzoic acid is stronger than benzoic acid and para-methoxybenzoic acid. So, this is regarding the cleavage of the OH bond in case of carboxylic acids. So, next we will have to discuss about the cleavage of the CO bond, reactions involving the cleavage of CO bond. So, the first reaction is formation of N-hydride, So, when carboxylic acids are heated with mineral acids like H2SO4 or phosphorus pentoxide, which is a dehydrating agent, a molecule of water gets removed. So, cleavage of one of the CO bond of one of the carboxylic acid takes place. So, the CO bond cleaves here, and this OH will combine with hydrogen atom, a molecule of water is removed, and hence it results in the formation of CH3, C double bond O, C double bond O and CH3. So, this is called as ethanoic N-hydride along with the formation of water. So, we have started with acetic acid. So, two molecules of acetic acid have undergone dehydration. So, you can see here there is a cleavage of CO bond in one of the carboxyl group. So, a molecule of water is eliminated, resulting in the formation of ethanoic, anhydride and water. So, the second reaction is esterification reaction. We have already studied about esterification reaction. So, carboxylic acids, they react with alcohols in presence of a dehydrating agent like any mineral acid or HCl gas as catalyst. It results in the formation of an ester. It can be an alcohol or it can be a phenol in presence of a mineral acid like H2SO4, or it can be HCl gas. It is a reversible reaction. So, it results in the formation of RC double bond O R dash along with water. So, here again you can see there is cleavage of the OH, a CO bond. So, this OH will combine with this hydrogen atom. So, it is removed in the form of water. So, then what is remaining is RC double bond O, O R dash, which is an ester. So, the next reaction is with chlorinating agents like PCl3, PCl5 and thionyl chloride. Reaction with PCl3, PCl5 and thionyl chloride. So, here the OH of the carboxyl group, it behaves like the alcoholic OH group. So, this OH group can easily be replaced by the chlorine atom of these chlorinating agents. So, first we will treat it with PCl3. So, the product is RCOCl. The OH is replaced by one chlorine atom and hence it forms PO. So, here 3 molecules of RCOOH reacts. So, we get RCOCl and H3PO3. So, this is called as an acid chloride and phosphorus acid. H3PO3 is phosphorus acid. So, next is the reaction of carboxylic acid with PCl5. So, here again the OH group gets replaced by one chlorine atom. So, it forms RCOCl along with POCl3 and HCl. So, this is again acid chloride and this is phosphorus oxychloride. One more reaction, it is with thionyl chloride RCOOH reacting with SOCl2. So, the product will be RCOCl along with the liberation of HCl gas and sulfur dioxide gas. So, again here the product is acid chloride. Main product is acid chloride. There is liberation of HCl and sulfur dioxide. So, this is the most preferred method to obtain acid chloride using chlorinating agents. That is because the product can be separated easily. These are all escape, they can escape, and hence you get acid chloride easily. So this is the most preferred method for the preparation of acid chlorides using chlorinating agents. So the next reaction is reaction with ammonia. Reaction with ammonia. Carboxylic acids, they react with ammonia. On heating, they form RCOO NH4. That is, they form the ammonium salt of carboxylic acid. So this on further heating, it loses a molecule of water. So there is NH4 group here, NH4 plus. So two atoms of hydrogen and one atom of oxygen is lost. So it forms R C double bond O NH2. So it gets converted into an amide. So we will take CH3 COOH and we will treat it with ammonia. So we get ammonium acetate CH3 COO NH4 plus O minus. So this is called as ammonium acetate, and this on heating will lose a molecule of water to form acetamide. That is R C double bond CH3 C double bond O. So we will write the reaction for acetic acid CH3 COOH reacting with ammonia. You heat it. So CH3 CO minus NH4 plus is formed. This is called as ammonium acetate, which on heating loses a molecule of water. It forms CH3 C double bond O NH2, which is called as acetamide. Similarly, you can write a reaction for benzoic acid. Benzoic acid, when treated with ammonia, it forms ammonium benzoate C6H5 COO minus NH4 plus ammonium benzoate. So this on heating, it loses a molecule of water. So two hydrogen atoms from this and one oxygen atom from this is lost. So it forms C6H5 C double bond O NH2, and this is called as benzamide. Another example you can take is starting from phthalic acid. Phthalic acid is benzene ring with two carboxylic groups attached to it. So heat it with ammonia. So then you get then on heating it strongly, it is going to lose 2 molecules of water. So, 1 molecule of water is lost from here and 1 molecule from here. So, you get this compound. NH2 and this is called as phthalimide. And this on heating it strongly, it loses a molecule of ammonia, that is NH2 group along with a hydrogen atom is lost, leaving NH, which links the 2 carbonyl groups. NH. So, this is called as phthalimide. This is phthalimide and this is called as phthalimide. So, here we get the ammonium salt of phthalic acid. Ammonium salt of phthalic acid. So, what you are going to do is phthalic acid, you are going to heat it with ammonia. So, you get the ammonium salt of phthalic acid, further heat it, 2 molecules of water is removed. So, you get phthalimide. This on heating it strongly will lose another molecule of ammonia to form phthalimide. So, the next reaction is with respect to the carboxyl group, the reaction involving the COOH group, that is the carboxyl group. So, we have studied that primary alcohols on oxidation will give you an aldehyde and aldehyde on oxidation will give carboxylic acid. But in the reverse case, when we subject it to reduction, that is when carboxylic acid is reduced, we get an aldehyde. This aldehyde further reduces to primary alcohol. So, here we are going to study about the reduction reaction. So, reaction involving the COOH group, in that the first reaction is reduction. So, we have studied primary alcohols on oxidation will give you an aldehyde. Aldehyde if further oxidized will give you carboxylic acid. Now, if the reverse process is carried out, then it is called as reduction. So, carboxylic acid will be converted into an aldehyde. Aldehyde will be reduced to primary alcohol. So, here we are carrying out the reduction of carboxylic acid in presence of reducing agents like lithium aluminum hydride in ether, or it can be diborane B2H6 followed by the acidification. So, here the RCOOH group gets reduced to the aldehyde group, but the reaction is very fast. You cannot isolate the aldehyde here. So, it directly gets converted into primary alcohol, that is RCH2OH. So, diborane can be used for the reduction of carboxyl group to the alcoholic group, but it cannot be used for the reduction of the halo group, the ester, nitro groups, etc. And even sodium borohydride, this cannot be used for reducing carboxylic acid to primary alcohols. So, the next reaction is decarboxylation reaction. decarboxylation reaction. So, the name itself suggests that there is a removal of a molecule of carbon dioxide. So, when the sodium salt of carboxylic acid is heated with soda lime, a mixture of sodium hydroxide and calcium oxide in the ratio of 3:1, we are going to heat it with the sodium salt of carboxylic acid. So, the product will be a hydrocarbon along with the formation of sodium carbonate. So, here carbon dioxide is removed in the form of sodium carbonate. So, that is why we call this as a decarboxylation reaction. So, one more thing you can notice here is when I take this compound, that is the sodium salt of acetic acid, and I heat it with soda lime. So, I get CH4 as the hydrocarbon. So, the hydrocarbon that is formed will have one carbon less than that of the corresponding acid or the salt of the acid. So, you can also carry out decarboxylation reaction by Kolb's electrolytic method, which we have studied in the first year. So, next is the reaction involving the hydrocarbon part. So, we have already dealt with the reaction involving the cleavage of OH bond, the reactions involving the cleavage of CO bond, the reaction with respect to the carboxyl group, that is two reactions we have seen just now, that is reduction as well as decarboxylation, and now it is the reaction involving the hydrocarbon part. So, the first reaction is halogenation. When a carboxylic group has an alpha hydrogen attached to it. So, this is a carboxyl group, this is the alpha carbon atom. So, it has an alpha hydrogen atom attached to it. It can undergo halogenation reaction at the alpha position in presence of chlorine or bromine with a small amount of red phosphorus to give you alpha halocarboxylic acid. So, we are subjecting it to halogenation in presence of halogens, that is X here is either chlorine or bromine along with a small amount of red phosphorus. We are going to heat it. So, the product will be RCH X COOH. So, this is called as alpha halo carboxylic acid, and the reaction is called as Hell-Olhard-Zielinski reaction. This is called as Hell-Olhard-Zielinski reaction, which we usually represented as HVZ reaction. So, this is regarding the reaction involving the hydrocarbon part. So, the next thing is the ring substitution reaction. So, in aromatic carboxylic acids, you can see that it undergoes electrophilic substitution reaction.